This is the trick behind fast lexical retrieval. Skip most documents without changing results. This is the workflow you'll know how to run when we're done, which builds a small index and finds the top results while skipping unnecessary scoring. I'm Professor Pi, teaching search and IR with simple Python. Search engines must find the best documents fast. When your collection has thousands or millions of documents, scoring every document for every query is too slow. Block Max Wand is a technique that prunes entire groups of documents using a cheap upper bound, so you only score the ones that could actually make the top list. That keeps results exact, while cutting work by large factors on real collections. At a high level, the idea is simple. Compute a per block maximum possible score, and use that to skip blocks that cannot produce a better result than the current threshold. You keep the full scoring formula for the few candidates that survive. The strength is exact top K with much less computation. A weakness is some pre-computation and slightly larger index metadata. We will build a tiny demo that shows the full flow. You will see a toy inverted index, compute BM25 scores, measure a naive scoring workload, build block maxima, prune candidates, and then verify the pruned pass returns the same top results. No heavy libraries, just clear data structures, so the concept is obvious and transferable. Now, we will create the tiny inverted index and compute a simple BM25 IDF. This snippet creates a toy inverted index in the variable post with 2 terms and a few postings. The variable n holds the collection size, which we use inside the function IDF to compute the BM25 inverse document frequency. The function IDF takes a term and returns the standard BM25 IDF with document frequency smoothing. We then evaluate the IDF for the term wand, round it to 2 decimals, and store it in W. Finally, we print the IDF value to show the relative rarity of the term in the tiny collection. A higher IDF indicates stronger discriminative power, which directly influences ranking. Next, we will add document lengths and a BM25 scorer and run a small query. This example adds a BM25 postings list and defines document lengths in DL to support BM25 normalization. The variable Q holds the query terms, and docs is the set of candidate document IDs from the relevant postings. The function SC computes the BM25 score of one document, but summing per term contributions using the IDF function from before, and standard K1 and B values folded into the expression. We then sort candidates by score, break ties by doc ID for stability, and take the top 2. Increasing average length would slightly reduce contributions for longer documents, shifting which doc appears second. The printed list shows the best scoring documents for this query. Now we will count the naive scoring cost so we can compare later. This snippet materializes per term frequency maps in the variable m for fast lookups. The variable docs is the union of document IDs touched by the query's postings, ensuring we consider only relevant candidates. We compute ops as the number of non-zero term contributions that the naive scorer would evaluate, effectively counting how many postings entries across query terms must be scored. This simple metric is a proxy for scoring cost in a document-at-a-time pipeline. If the query had more terms or longer postings, ops would grow proportionally. The printed count is our baseline workload against which we will compare pruning. Next, we will build fixed size blocks and compute block maxima to prune safely. This snippet partitions documents into fixed blocks in the variable B and computes a block level upper bound UB as the maximum document score in each block. We reuse SC to approximate pre-computed block maxima. In a real engine, these are stored at indexing time. The variable top holds the naive top K result, and tau is its current threshold. We then form S by selecting only documents from blocks whose UB meets or exceeds tau, which safely retains any candidate that could enter the top K. Finally, ops pruned counts the term contributions evaluated only within retained blocks. The reduced count demonstrates pruning power through block level maxima. Now we will rescore only the retained documents and check correctness. This code recomputes the top K over the pruned candidate set S to validate correctness. The variable ptop holds the block pruned top results using the same scoring function SC and deterministic sorting. The variable same checks equivalence against the naive list top obtained earlier, ensuring that pruning did not alter the outcome. If K increases, tau becomes tighter after selection, and more blocks may be retained, which can increase scoring work while preserving exactness. Conversely, decreasing K often strengthens pruning. The printed list shows the final top K produced by the block pruned pass, confirming it matches the naive baseline. Applied to a real system, this same pattern maps cleanly. Partition postings into blocks at index time. Store per block maxima. At query time, use the maxima with a running threshold and only score documents from promising blocks. That keeps top K exact, while cutting scoring by an order of magnitude on medium and large collections. Recap what it is: a block-level pruning strategy that uses pre-computed block maxima to skip scoring safe groups of documents. When to use it: when you need exact top K from a lexical scorer like BM25 and want much lower latency on large collections. One caveat: you need extra metadata and careful block design to get strong speedups. Next step: tune the block layout and the BM25 normalization constant to see how pruning and ranking interact. Try larger block sizes and different average length normalizers to measure trade-offs between index overhead and scoring savings. If practical IR and faster top K matters to you, subscribe and watch the rest of the IR videos.